second speaker of this afternoon is the Professor Rezende from the Unicamp, and he's talking about dynamical spectral sequences in Conley's theory.
Okay, thank you. I'd like to start by thanking the organizers for the invitation. As Diogo said, it is also an honor for me to be here celebrating Mauricio's 90th birthday. Mauricio has known me for what, 50 years, Mauricio? Not many people can say that, right? So it's really very nice to be here. Okay, so today we're going to speak about dynamical spectral sequences in Conley's theory. And I think Etienne mentioned that any good talk should have at least a proof. This one won't. And the reason being, well, not to say it'll be a good talk, I hope it will, but the reason being is that spectral sequences have a very bad, let's say, reputation in mathematics sometimes. And it, in fact, the excessive amount of indexing can be a little frightening. So if you can leave today here with a little better impression of spectral sequences, I think I was successful. So let's try to pass on this, this view of spectral sequences. So we're going to, the outline we'll follow is a very quick just go basic definitions, actually Morse theory, because the Conley theory is more in the generalization, which we won't be able really to talk about. Then we'll talk briefly about spectral sequences, a method we developed. This is work with Octave Cornea and Mariana Silveira. And then we'll talk about what we call the Conley spectral sequence, which has a dynamical motivation behind it. And here we go into, we're starting to apply this to study bifurcations and in the future, in the Conley theory, to study a continuation. Okay, so this is essentially a diagram of what we have. We're working, let's just think of the critical points of a Morse function, and we can get to this Morse decomposition later. Chain complex C, and from this chain complex we really want to talk about what we call a connection matrix, which comes from the Conley theory, and spectral sequences, and the method we developed to connect these two objects. Okay, so a Morse, let me go really elementary. We have a Morse function if all the critical points are non-degenerate, or if we have these local coordinates, the Hessian matrix is non-singular, K is the Morse index of X, and then we have the associated gradient flow, and I'm going to assume that it's Morse-Smale. So the connecting orbits, if I have x, y critical points, I'm going to call the connecting manifold between x and y by mxy. So we can see that in green there, for instance, between x and z. And then I want to consider a regular value between f of x and f of y and call the moduli space between x and y as the intersection at a level set. Okay? And then we know that the dimension of the connecting manifold is always the index of x minus the index of y, and of the moduli space 1 less. Okay? Yes? Okay. Yeah, it's actually the moduli space I'm taking as that level set. See the blue, for instance? That would be the moduli space corresponding to the connecting manifold from x to z. It's really when we quotient out the flow lines. Some people use the definition that the moduli space is actually the collection of the flow lines. That's fine. They're equivalent definitions. And actually, we'll be working with zero-dimensional moduli spaces for this talk. There's a student working with higher dimensional moduli spaces, but we're not going to even get close to that. Okay? So, all right, so so what do we need here? And why am I going through this, by the way? I'm going through this very quickly because I want to make the connection of this classical theory with the Conley connection matrix. Okay, so we're going to really get from this the Morse-Witten complex, which is what I need. Okay, so quickly we're going to give an arbitrary orientation for all the unstable manifolds for the critical points of this Morse function. And then I'm going to say that this connecting space inherits an induced orientation. Okay, and the idea is the orientation on the tangent spaces of the unstable manifold are chosen arbitrarily. I think one can here see, so it's an arbitrary orientation here, an arbitrary orientation there, and then by this isomorphism I have here the this orientation restricted to the connecting space. Here I have the normal to the connecting space, the normal to the stable manifold, so I have an orientation. And these two orientations which are defined induce an orientation here. So for instance here, this orientation is for this space, and this one is for this space. And so when I have this orientation, I complete so it's compatible with this one. Okay, so from there, I have the orientation that's induced on the connecting space, which is this green space here. So actually, if we look at this picture, the orientation induced on the connecting space is the one in red, and we have the connection that's given by the orientation that's given by the flow lines themselves. So from there we can define the induced orientation on here, the induced orientation on the connecting space, the orientation induced on the tangent flow, and the characteristic sign, which compares those two orientations. So if I compare here, they're in the same direction, +1, they're in opposite directions, -1. So this characteristic sign is essential for what I want to define. Okay, so the graded Morse group is associated to a Morse function with integer coefficients. So here we'll be working with integer coefficients, and graded by the Morse indices k. It's a free abelian group generated by the set of all critical points of f of index k. So this is, you can also see this as a Z module, and it's just the sum of all these spaces here. Okay, so these are the sets we'll be working with. Okay, the kth Morse-Witten boundary operator then is defined from Ck of f, all the critical points of index k to k-1, and is defined on these generators of Ckf. Okay, so the boundary operator, remember we just defined, we just defined this characteristic sign. So the boundary operator gets a critical point of index x, associates the total sum of these NUs, which are sums of plus or minus ones, and y is the k-1 critical point. So that's how the boundary operator works. And of course, this is always extended to all the chain by linearity. Well, we're working in a finite dimensional context, but this turns out that in this finite dimensional context, it's exactly Morse-Witten's theory. Morse theory. Perfect. Yeah. For now. But we want to open possibilities, right? Many open questions here. Okay, so this Morse-Witten operator can be visualized as a matrix delta, which contains these matrices delta k. Okay, and this, each one of these delta k's has the property, and here I put for all these the giants before Witten, from which Witten's work flourishes, all have had a hand in theorems like this. So this is the theorem that guarantees that this Morse homology over Z is actually just the singular homology. Okay, so this chain complex, C delta, with that matrix, which is, the chains are just generated with all the critical points, and this operator, this matrix delta, which I just showed you, is called the Morse-Witten's complex in this case, and the matrix delta represents this special case of a connection matrix. Okay, DM, we'll talk about it later, is just the decomposition of the Morse decomposition that we use in Conley's theory. But for us, it's just the collection of all the critical points. Okay, so here in the same example we just showed, we have the chain groups generated by the index 2 critical points, the index 1, the index zeros. So here are the chain groups. We have the ends, which we need to define the boundary operators. Okay, so this is just to illustrate what we have. However, we can see the same situation by writing the matrix of all the nxy's. So here we have nxy 0, so x to y is 0. The nyz, y to z, is -1, and y to z prime +1. So this is the connection matrix we work with. Okay, so it contains the same information of the Morse-Witten complex, of the operator of the Morse-Witten complex. Okay, we can also look at this with homology coefficients in Z2, and actually for some of the dynamical interpretation that I need, it's we don't really have the complete information over Z because there's torsion that appears and we don't know how to interpret that dynamically. So the dynamic interpretation we'll see later on will be over Z2 and not over Z, although the theorem, the main theorem, holds over Z. Okay, so suppose X and Y are hyperbolic rest points with, I'm sorry, I left this. Just think Morse index K plus 1 and K. That unstable manifolds are transversal. Then the flow-defined map delta xy counts the number of connecting orbits from x to y mod 2. So that's how we would use the matrix here, not over Z, but over Z2. Okay, so spectral sequences is just a sequence such that the ERs are bigraded modules, that is an index collection of R modules. R is a principal ideal domain for us, it's just Z. We just worked over Z. DR is the differential of by degree minus R, R minus 1. And that is the collection of homomorphisms from, and that's where this thing starts getting messy, right? From ERPQ to ERP minus R, Q plus R minus 1. We're going to try to bring in a visualization of this so that it doesn't look that bad, and such that dr squared is 0. Okay, and what's interesting is that that the homology of each ER is the next module ER plus 1. Okay, and here are the formulas that give us the homology, the kernel of dr and the image of dr. Okay, so we can think of this, each of the modules ER, so we can think of this as a book with pages, and the differential has by degree 0 minus 1, so so we go 0 in the x direction and minus 1 in the y direction. So that's how we see the D0. If we go to D1, it has by degree minus 1, 0. So we go minus 1 in the x direction, 0 in the y direction. Okay? And so forth. The differentials get longer and longer as R increases. Okay, and this is another way to see exactly what we have. When we look at this direct sum of the modules ERQ, the differential DR defines a homomorphism from ERQ to ERQ minus 1. So if we look at this diagonally, then we have a chain complex where the differential of the spectral sequence is really just the boundary operator in this new chain complex. So the homology at this stage of this is just the homology of the direct sum here along the diagonal. So that's a nice way to visualize that property. Okay, so let's go back to our context. We have this Morse chain complex. We're going to introduce this filtration, an increasing filtration, because we want to compute a spectral sequence of a filtered chain complex. So we need this notion of filtration. So an increasing filtration FNC is just a sequence of submodules, FPC for all P, such that F of PC is contained in F of P plus 1C. Okay, and so CK is just a graded, if CK is a graded module, the filtration is always compatible with the grading. So this is the ingredient we have. We have the Morse chain complex and we have a filtration. And from there we get a spectral sequence. So this is a classical construction. It took us quite some time studying the last chapter of Spaniard's book to understand this in our context. So if we have the Morse-Witten complex, here are the chains generated by the critical points, the boundary operator in the form of this connection matrix. Then we want to associate a spectral sequence to this. So we need a filtration. In the matrix, how are we going to look at this filtration? We're actually going to look at the columns from right to left. So remember, the idea here is to give a combinatorial way of understanding on the connection matrix what is the spectral sequence. So the filtration is given by the columns. So there's a shift in index. That's our fault, but it's supposed to be like that. So there's a shift by 1, but in any case, FP of CK starts in column P plus 1 and covers all the singularities of index K to the left, in the columns to the left. So we can define a filtration. We can see the filtration actually on the matrix. Okay, and here this is what terrifies people, is to look at these formulas. You know, you look at these formulas and say, what does this mean, right? And if we think of these H's as just the critical points of index P plus 1, P plus Q plus 1, here a collection of P plus Q's, here mixed up other indices, the filtration, an arbitrary filtration here, you can see here on the left. What are these formulas saying? They're just saying that you're going to look at the chains that are in the filtration F of P of index P plus Q. So you're going to single them out such that their boundary falls into the FP minus R. So it's awful here. We don't quite see it. But let's say that this one is in that space, because if we look at this connection, I'm representing the connection with the green, the boundary falls right into here, into FP minus R. So this would be an example of a critical point that's in this space. And then we have to look at the quotients, the similar idea of these connections. And these connections, as we've seen, are actually connections in a gradient flow. So we're starting to look at this, thinking of a gradient flow and their critical points and their connections. Okay, so these formulas have a sort of flavor of dynamical systems and gradient flows and connections. Okay, so however, what we want to do is work with what we call a finest filtration, so that we have one critical point in every FP minus 1, a unique critical point. So So this is the case of what we'll be working with. We'll choose a finest filtration, and we'll have exactly a critical point in each, let's say, in each 2 consecutive levels. Okay, so the formulas have let's say, a particular way of looking at them. Okay, so I'm just going to pass this on quickly. So what did we develop? We developed a method, a method that it's actually just an algorithm that is going to sweep the connection matrix. And what's amazing, at least for us was amazing, that this procedure of sweeping the connection matrix really gives us back the spectral sequence. So once again, looking at the global picture, we have the Morse flow, we have the chain complex, we know what a filtered, what the spectral sequence of a filtered chain complex is, and now we want to get that connection matrix, which is here, associated, it's the boundary operator of this chain complex, is the connection matrix, and we want to produce a family of matrices through this sweeping method. And this family of matrices will give me back the spectral sequence. So it's a combinatorial way of retrieving all the information we have from the spectral sequence. So once again, let's try and look at the filtration and what this module is in the matrix. Since we're looking at all chains from column P plus 1 to the left, that's what we see here. That's the ZRP. The ZR minus 1P minus 1, exactly the same thing. We're going to look at the filtration P minus 1. So all of these to the left. So we're quotienting out this plus this, which are the critical points that the image comes into this, which we saw in the other graph. So these formulas really can be seen in the matrix in some sense. So it's natural that we work with this matrix to try to retrieve the spectral sequence ERP and the differentials. Who are the differentials? So what we're really going to do as we sweep the matrix to produce a family of matrices is we're going to be changing bases all the time. But how we change bases over Q of these integer matrices. We start with an integer matrix, we change bases, and we start producing other matrices which might not all be integers. And you could have rational entries. Okay, so we're going to do the sweeping method. And so what is the sweeping method? We're going to mark certain pivots with the diagonal as we sweep the matrix and perform change of bases that the let's say, prompted by these pivots. So we'll produce a sequence of matrices delta R through this change of basis, and T is determined by the pivots of delta R, the change of basis matrix. And the pivots really determine T and also induce the differentials. All of this over Z. So an example. We have a matrix. So remember, all of this are those n xy's that we saw. Those we summed up, and so it's just an abstract example. Let's see how the sweeping method works. So we mark pivots. We call these the primary pivots. Once the diagonal touches, they're auxiliary diagonals that are going to sweep the matrix. Next, if we mark those in blue, are called the change of basis pivots. So the primary pivots, they just have the property that they have these zeros to the bottom, zeros to the left, zeros to the bottom, zeros to the left. The change of basis pivots are always next to a primary pivot. So as we sweep the diagonal, we identify these change of bases, and they will prompt us to perform a change of bases in the matrix. So we always try to have linear combinations over Z of the columns. It zeroes out the entry of the change of bases pivot. The purpose is to make that change of bases, the blue pivot, be turned to a 0, and we'll see that now. And also respects the filtration. We're always from the left to the right. So for instance, down here, we want to zero out this entry, right? So what we're going to do is we're going to get this one times 3, this one times 2, and in the next step here, this will be zeroed out for this column. So of course, all of this has to be put in a matrix T that performs the change of bases. And as we perform the change of bases, it will be registered in these sigmas, this operation that we're doing. Okay, similarly here, we just sum the two to get a 0 for the change of bases. Okay, so here we just sum the left column to the right column. And notice how the next step on the third level, this is the second level, is just the sum of the two columns. And this will be the new, this basis to keep track of what we're doing. These sums are important. Okay, and so we continue to just sweep the matrix. Notice that we produce the two zeros we wanted. And again, as we sweep, to the left we have a change of basis pivot. To the right, a change of basis prompted by these primary pivots. And look at the rational entries that are starting to appear here in this matrix. And we go on, sweeping the matrix, performing these change of basis. And if you notice what's happening, we're really producing a lot of zeros here, as if these will represent orbits that don't disappear anymore. They're like, throughout the whole process of the sweeping, they're like permanent orbits. They won't, if they represent orbits in a gradient flow, these don't disappear. And then we continue to perform this sweeping method and until all changes of bases are gone, and we have this final matrix just with change of basis pivots. And notice that we have all this registered in the matrix. What were the operations that got us to this final matrix? It's interesting to notice that the final matrix here has no rational entries, and that intrigued us. Why is it that we weren't finding rational entries? And later, because we don't know how to interpret the rational entries in the middle of this process. I mean, if these matrices are actually n of xy, what is n of xy equal to a rational number? I don't know. If any of you can help me have a better idea, it would be interesting. I don't know. So it doesn't mean anything, at least to me, dynamically. However, the final matrix is always integer, and that was proved in some recent work with Margarida Melo, and she actually brought it down to the fact that these pivots in the change of basis, they had certain invariant properties, and she brought it down to an integer linear problem and was able to prove that the final matrix is always integer, which is quite surprising. At least for us it was, because we noticed it would happen in some examples, but we didn't know how to prove it. Okay, and then, so the goal of the sweeping method is to code in a combinatorial way the information of the spectral sequence. The sweeping method applied to delta will give us then the following results, which is why we call it the Conley spectral sequence. So the sweeping method applied to this connection matrix will give us the generators of the modules ER in the spectral sequence. It will tell us certain entries will tell us how the differentials dr of the spectral sequence are induced, and it also is connected with paths in a flow associated to the connection matrix. So there are several results that come from this sweeping method. Here is the implementation. It was done, there's a program available. It's done in Mathematica. Not only it generates these matrices, it does this whole sweeping. It produces all the homology, torsion, whatever, through, it's a program, it's in Margarida Melo's domain. She actually wrote it, and it's a great tool to test certain conjectures, to see if things are as we expect. And the integrality of the entries in the last matrix produced by the sweeping is also in a work with her. Okay, so the Conley spectral sequence then has exactly are these results I just mentioned. Just to wrap this up, we have the matrix delta R, this connection, these collection of connection matrices that are obtained at each stage of the sweeping method. So the matrix delta R will determine the generators of the module ER, of the module ER of the spectral sequence. So each matrix delta R will tell me what this module, what this Z module is, plus the differentials in the spectral sequence. Whenever this space, ERP and ERP minus R, are both non-zero, then the entry corresponding to these indices in delta R is either a primary pivot, a change of basis pivot, it's either the red one, the blue one, or just a zero with a column of zeros below it. And in each case, they induce a differential. So if ER, and this is exactly what this is saying, if ER and ERP minus R are both non-zero, this map, the differential, is induced by delta RP, that is by multiplication of this entry. So that's how this entry induces this differential. So here is the spectral sequence. Since we have a finest filtration, notice that each column of that book only has one generator, one critical point. So I really don't need a two-dimensional representation. I can represent each page actually linearly. And so the change, the primary pivots here induce the differential. So you see these primary pivots, what happens at the next stage, it zeroes out the domain here. The change of basis pivots also change the base of the domain and zeroes out the image. So we have several properties. There are also other more technical properties. We have to sometimes check the maximal MDC here between 3 and 2. There are lots of other technical properties that have to be checked. But at the end, look, this is E2, E3, E4. At the end, it converges. So these spectral sequences always converge strongly. And, but then again, for integers, we don't really know how to interpret the torsion that appears. So we don't know dynamically what this means. So to start to get a dynamical interpretation of the spectral sequence, we brought this down because, as you see, we have torsion appearing. Certain things here is interesting. For instance, every time we have a plus or minus 1, it's really Smale's cancellation theorem. It zeroes out both critical points. So here, look, 0, 0, and the differential is minus 1. Here, 1, 0, 0 at the next stage. So Smale's cancellation theorem appears here whenever you have 1. But what about the other ones? When you have multiplication, torsion appears. What does that mean? We don't know. Okay, and whenever we have a zero, a column of zeros, what happens at the next stage is that nothing changes. If you look at the formulas of the kernel of dr, that's over the image, that's what we would expect. Okay, and so now to understand a little bit of the dynamics behind this process, we're going to restrict ourselves to Z2. So we'll talk about the connections here. These are the family of matrices we obtained from the sweeping method. Here are the change of bases at each stage. And these are called, actually in Conley's theory, they're just called transition matrices. And where we're getting at is that these transition matrices really give us the points where the system can undergo a bifurcation. They're just, it's really a family, a continuation that we see. So for instance, if we have this is the classical example in Franzosa's paper. Actually, we've been working with him on this. And so here we have this system, the orbits, lambda near zero, large lambda, lambda equal to lambda star. So we have these phase spaces, but let's just represent them a little more schematically so we can look at the matrices. So here we have the connection M3, M2, and M1. So it's always from right to left. So M3 doesn't connect to M1, right? I hope I have these right. And M2, which is this, connects to M1. Here's the connection. Similarly here, I have M3 connecting to M1. I also have M2 connecting to M1. M1 is represented here by H0. It's the sink. So we have those two ones representing these. Okay, and then we can look at the matrix here and sweep. This is a very simple example, but we can sweep the matrix just by adding. We obtain a zero here. Okay, so the idea is that once we identify this change of basis, to get from this matrix here to this one, we have to perform a change of basis. The change of basis will involve adding this column to this one to zero this out. And that's the one who's going to be responsible for this saddle-saddle connection. So the change of basis matrices, which are called transition matrices, are the ones that are going to produce saddle-saddle connections. So here's just an example. If we have these four connections here, and we want to sweep, we have a change of basis here to produce this zero. So in the middle stage, since we have to add this column to this column, the H4 we have to create a saddle-saddle connection between 4 and 3. So in this sense, this is another way of seeing it. Whenever we don't have transversality, it's as if this dynamical system, let's just call it, has multiple connection matrices. When transversality is satisfied, we have a theorem of Reinach that guarantees uniqueness of the connection matrix. So essentially what we're doing is, as we sweep, we're producing new dynamical systems by changing the connections. So here's another way of seeing it. This one becomes a saddle-saddle connection, and then it just moves on again to satisfy a transversality condition with the unstable manifold now connecting to something else. So what are we saying? That this sweeping method is actually describing a family of gradient flows that undergo bifurcation, and we know exactly what the connections of the saddles are. Okay, so let me just go past by these quickly and just show you this dynamical interpretation then. So delta is a connection matrix over Z2 associated to this set of critical points, decomposed, let's say, in this finest filtration. Okay, so we have the collection of connection matrices. We have these diagrams that you just saw, and each one will be obtained from the previous one through this process which we refer to as topological continuation, which is this bifurcation, intermediary bifurcation situation. Okay, so here is an example, for instance, for a larger matrix. As we sweep, we have the change of bases. These are supposed to induce these orbits, which will become saddle-saddle connections. So at the next stage, here are the change of bases produces these two ones, and unfortunately I couldn't put but this is of the same index as this one here, because it'll be a saddle-saddle connection of the same index. So there it is, saddle-saddle connection that it produces. And then at the next stage, what we're going to see is new orbits now from here, from H11 to H7. So, and there it is, for instance, from H11 to H7. And it goes on. New future bifurcation orbits will be this one. As you sweep the matrix, you produce these diagrams, and we know where the bifurcation will occur, and so forth. So there it goes. So that was our intent, was to actually bring down to the simplest case, which are the gradient flows, to try to understand what these connection matrices actually can give us as dynamical information. And we see that it's nothing but in the case over Z, then the Morse-Witten operator. We developed this algorithm which, let's say, recuperates the whole spectral sequence, all the differentials, yet we don't have a full dynamical understanding of these differentials, what they mean in terms of these paths which we have in the case of Z2. We can see that it's a bifurcation that's occurring. However, over Z, we don't know what's happening except in the simple case due to Snell's theorem when we have the differential being plus or minus 1. Okay, and just to wrap up, why do we call this the Conley spectral sequence? Because our intent was exactly to be able to use this in a more general context. The Conley index is, let me just go quickly over this, but the Conley index, you see, if we have an invariant set, we can call the maximal invariant set in here, of n. So we're on a compact neighborhood, and this invariant set S is isolated if there exists a compact neighborhood N of S such that S is the maximal invariant subset. And in this case, N is isolating the neighborhood of S. So in this sense, we have this, in this example, a simple saddle, our maximal invariant subset in this neighborhood is S. But we can have more complicated sets, and that's what we wanted to get to. We wanted to be able to describe connection matrices for a more general situation than just a gradient flow. So here the maximal invariant set in this compact neighborhood is S. And this is just a quick look so we can get to the idea of where we would also like to generalize. So we're able to define an index pair and an index. That's what's impressive. If we have an index, and in the case of the Conley index, what is our index? Our index will use a pair of spaces where we have an exiting set, the invariant set here, and we will look at the quotient space. So once, and the main theorem is that this quotient space is actually, it doesn't depend on the choice of the index pair we choose for the invariant set. So it is an invariant of the maximal invariant set. It's actually, it's the homotopy type of this quotient space. So we just have to identify the exit set. So here are examples of a saddle. We identify the exit set to a point, and then since we're looking at the homotopy type, if this whole thing is identified to a point, we're left with an annulus, which is homotopy equivalent to S1. So that's the index pair. Here we can also define the space, which would be the index. So remember, the index, the Conley index, is the homotopy type of a space. So, so here we have the index pair. It doesn't matter which index pair we choose for our invariant set S. This homotopy type of n minus is what we call the Conley index. Now, how do we get to the matrix from this? We have to look at the homology. Since this is a homotopy invariant, we will look at the Conley homology. And by looking at this Conley homology, and here I won't get into the definition of the connection. Here, see the spaces, which are the indices associated to the invariant sets, are there. But I can look at the homology and the ranks. So I have numbers here. And these numbers will eventually, let's say, get into the connection matrix somehow. And then the most important property of the Conley index is this invariance by continuation. So the index of this invariant set is the same as this one, which is the same as this sink. They all have the same Conley homology index because the index is invariant under this continuation. If we can isolate the invariant set in the same neighborhood, of course, if the index is the quotient of the neighborhood in its exit set, then it doesn't matter what we have in there. Okay, so a Morse decomposition of our manifold then will be this collection of these Morse sets, which are just mutually disjoint compact invariant subsets of M, such that if I'm on any point on the manifold, M minus these Morse sets, then this point is always in a connecting orbit from some Morse set to some other Morse set where P is less than P bar. So the invariant sets, let's say the maximal invariant sets, which we just talked about, we want them to be here in the Morse sets. So what we talked about in the beginning of the lecture here was about this situation where each Morse set was really just a critical point. It's a very simple situation, simple, quote unquote, because we still don't understand all the information we have, even in this case. And what we'd like to work with are matrices that are coding, here, this is schematic, of course, but which is coding a more richer behavior. And for that, the idea would be to look at filtrations which are actually coarser filtrations. So that's one way that we're looking at this generalization. And of course, the other way to understand further is also to look at higher dimensional moduli spaces under this, under the spectral sequence technique of the sweeping algorithm. But then we have to have the entries that will be going above those blocks that you saw in the matrix. The next blocks would would actually carry information from higher dimensional moduli spaces. But that's way in the beginning, and we still don't know how to deal with that information. So that's it. Thank you very much.